We finished with the groups last time, and I hope I managed to convey the nice properties of the abstraction we get by starting from simple arithmetic and coming to groups. Now today I'll start on the next abstraction, which is called rings. Now rings are perhaps the single most important abstract object in whole of mathematics. It is extremely fundamental, extremely useful, and is applied in a very wide variety of domains. And the reason, at least one of the reasons for why it is so important is simply that it very nicely abstracts almost the whole arithmetic. So if you recall, if we go back to our motivating example of numbers. Numbers we know admit two operations, addition and multiplication. And then when we abstracted out groups from them, we said, okay, let's just focus on one of those two operations. Now in case of rings, we abstract or try to abstract the full arithmetic, which means simultaneously abstract out both the operations and the way they interact with each other. Now if you see the set of numbers, the addition and multiplication operations satisfy certain properties. And we can express those properties in terms of the abstraction we already have. For example, in a set of numbers, let's say x is a group under addition, right? Whether we start with x being a set of integers or set of rational numbers or set of real numbers, etc. It is a group under addition. And again, when I say group, I mean a commutative group. In fact, that's the reason why we abstracted out the group structure to begin with. Now, what can we say about this set under multiplication? For some of these sets, like real numbers or rationals, the non-zero numbers form a group under multiplication. We have also seen that. But it is not true in case of integers. In case of integers, we don't get a group under multiplication. And I won't at this point like to leave out integers from the picture because I want to abstract out this arithmetic in a most general possible way. You can do arithmetic on integers, but it is somewhat more restricted in terms of division not being there, or only part of the division being there. We can divide 4 by 2, but we cannot divide 4 by 3. So in that sense, one would like to abstract out the most general arithmetic structure. And because of that, I would not say that this set of numbers is a group under multiplication, but it does satisfy all other group properties. Namely, x star, I should say. X star means x minus 0. Under multiplication, it is closed, it is associative, has an identity, and it's also commutative. The only property missing is the inverse. Okay. So that's the structure of these numbers under multiplication. We already know the structure of numbers under addition. But there is one thing that is still missing is the way addition and multiplication interact with each other. And that is captured by the next property. This is called distributive property. And this property captures the way when we do addition and multiplication simultaneously, what happens. So A multiplied with B plus C, this number, is same as A multiplied with B and A multiplied with C added to it. So these three are the properties we can abstract out when working with any set of numbers. And this is what is a ring. Let me say, okay. Almost exactly the same set of properties that I had listed earlier, with one minor difference, which is that I have removed the commutative property for the multiplication operation. And depending on whether multiplication is commutative or not, the ring will be a commutative ring or not. Sorry, plus star, of course. So structure R under addition and multiplication is commutative ring. The multiplication operation is commutative. Note that addition or operation must always be commutative. We are not leaving any option for it to be non-commutative. And again, for the purpose of this course, we will be interested essentially in commutative rings, not in other types of rings. So whenever I say a ring without meaning either commutative or non-commutative, it will normally mean a commutative ring. So that's the definition, pretty straightforward. And now we can immediately ask examples of rings. Of course, integers, rationals, reals, complex numbers under addition and multiplication is a commutative ring. That's straightforward. That's where the definition comes from. How about other examples? You have any other suggestion? Matrices, absolutely, yes. If you look at, and there is this notation that is used here, let's use M n cross n to represent the set of all n cross n matrices under addition and matrix multiplication is a ring. It is not necessarily a commutative ring, because under multiplication the matrices not all matrices commute, so it is not a commutative ring. Okay, so that's a general ring. Any other examples? That's very nice. So what you're saying is a plus I root 2. What is I? Square root of minus 1. So what is the set of numbers you are talking about? A is from integers, okay, and I root 2. No, that a plus I root 2 won't make sense. Probably you mean a plus b root 2, where a and b are both integers. So that's indeed a ring. It is given a specific name z bracket square root 2, and it is contains of numbers of the kind a plus b root 2, where a and b are integers. Why is this a ring? This requires a little bit of work. It's not immediate. Firstly, it's group under addition. That's clear. What is the additive identity? That's 0, and the inverse, etc. is all. Inverse of a plus b root 2 is minus a minus b root 2. So it's clearly a group under addition. How about multiplicative property? What is identity is 1 for multiplication. It is closed under multiplication. When you multiply two such number, you will get another number of the same kind. It is clearly associative just by virtue of being, these are all real numbers. And similarly, the distributivity property also. So it is a ring. In fact, instead of root 2, I can have something else also. I can have root 3. Any irrational number, exactly. In general, I can have Z with alpha is the set of numbers a plus b alpha, a, b in Z, alpha, an irrational number. That's a ring. Okay, that's great progress. What about other examples? How about a set of polynomials? Let's say polynomials in one variable. So, shall we say z bracket x? This is a polynomial in one variable, so that is where aj is in z and d is a positive integer. So this is just a collection of all polynomials with integer coefficients in variable x. Is this a ring? Pretty obviously yes, because you can add polynomials, you can multiply polynomials. Under addition, it clearly forms a group. Under multiplication, again this expected properties of multiplication hold, and multiplication distributes over addition. That is, if you have polynomials p, q and r, then p times q plus r is same as p times q plus p times r. So again, it's very simple but nice example of a ring. And the good thing is we can already see this abstraction generalizing and giving or spanning a number of different types of structures. Polynomials, matrices, numbers, and numbers of different kind. We have this integers with irrational, one irrational number as well.
Sir?
Yes.
Sir, polynomial, how multiplication?
Multiply two polynomials. Sorry?
You can take power above capital.
Yes, yes. So it's not d is not fixed. D can be any positive integer. So multiplying two polynomials of degree d1 and d2 will give us a polynomial of degree d1 plus d2. And that is fine. And you are very right that if we restrict or put an upper bound on the degree, then it ceases to be a ring, because of the same reason that if you multiply two polynomials, their degree might exceed. Okay. So these are some very typical examples of rings. And for rings, the central question again is, what is the structure of a ring? Just like we had asked this central question about groups, what is the structure of a group? And then we could, in a large number of cases, explain the structure. That a group is several copies of Z. Not all groups, but finitely generated groups consists of several copies of Z plus a small piece which is the finite group part, and that also has copies of the kind Z p to the alpha for different primes p. So in the same fashion, we can ask, what is the structure of a ring? And again, we will not be able to explain the structure of all possible rings. That can be very bizarre. But we will be able to explain structure of a fairly large class of rings. And the clue to that again starts from the real original example of a ring, which is the ring of integers. Just like the group under addition for integers, in a sense formed or gave us the canonical example of a group. And that group we could find, or we could express other groups into form of this Z, several copies of Z, or Z quotiented with a subgroup. In the similar fashion, we would ask, in what way is the structure of set of integers reflected or found in other rings? Are you following me? No. So in case of groups, we found after some investigation that the group of integers under addition is perhaps the most basic type of group, the simplest type of group with one generator, and then we can express any finitely generated group as several copies of Z. Right? So, in that sense, the group of integers was the simplest group possible, and other more complex groups can be expressed in terms of this. So, the structure of the group of integers is found in a repeated or copied in multiple copies in any finitely generated group. And we ask the same question for the ring of integers. That firstly, what is the structure of ring of integers? Structure of group of integers is pretty simple. Under addition, it is a single generator 1 that generates the entire group. Okay. So, now that we have two operations, we will again ask what is the structure of the ring of integers, and then ask the question, is this structure found in other rings as well? Okay. So, first question that we must ask is, what is the structure of the ring of integers? So, now we have integers with both addition and multiplication operation, and there is a very nice structure that has been found in this ring, which is called the fundamental theorem of arithmetic. This is something you have come across already, that every integer can be uniquely expressed as a product of prime numbers. So, what is the proof of this? Do any of you remember? Firstly, one has to define what prime numbers are, which are the numbers which have no divisors except 1 and the number itself. So, we are talking about the notion of division, which only exists partially in case of integers. And so, for prime numbers are those which cannot be divided by any other number except 1 in itself. And if you can write, firstly we can write every number as a product of prime numbers. That is the first step one needs to carry out to prove this. Can you do that? That should be easy. I mean, I'll leave that to you. You don't have to think about it. You've already done it in the school. You can recall that proof. Similarly, one can show that if a number has more than one expressions as a product of primes, then these expressions or the primes in these are the same. So they cannot be two distinct ways of writing a number as a product of prime numbers. There is one thing which I forgot every m in Z which is positive. A negative number one has to multiply with -1, which is not exactly a prime number, and that we have to also use in the product. So every m in Z, m greater than 0 can be uniquely expressed as a product of primes. Okay. So that's the basic structure of the ring of integers. And we would like to know if in a general ring such a structure or a similar structure exists. Let's take an example. Firstly, this structure will only exist in rings where division is not fully available. If you look at a ring of rational numbers, there are no prime numbers. Why? Or let's look at a ring of real numbers. I claim there are no prime numbers in it. See, its proof is very simple. Suppose a number a, which is a real number, is a prime, then a by 2 is also a real number, and a is 2 times a by 2. So certainly not prime. So there exists no real primes. I mean, in the ring of reals, there are no primes. The ring of complex numbers, there are no primes. Similarly, ring of rational numbers, there are no primes. And the reason is the same in all three of them, that the division is available completely. So you can divide any number by any other number and get a third number. So that is something we will not really be looking at, because that doesn't quite mimic this, or cannot mimic the structure of the ring of integers. So let's restrict the attention only to the rings where division is not fully available. And further, I will restrict attention to only commutative rings. Okay. Now, with this setup, let's go back to the examples we had listed. What were the examples? 1 is already ruled out. 2 is not, because 2 is not commutative. What about 3? That's 3. 3, well, 3 is a subset of 4. So 4 and 5. These are the two rings. In both these rings, division is not fully available. Okay? So let's consider Z with root 2 to begin with. What is the structure of numbers in here? Does fundamental theorem of arithmetic hold? Well, in order to see fundamental theorem of arithmetic hold, we have to define the prime numbers in here. What are prime numbers in this ring? 3 a prime number in this ring? Or let me ask, is 2 a prime number in this ring? 2 should be a prime number in this ring. Why?
It takes A and D both can be prime. Everything can be written in.
No. So in order to show that 2 is prime, by definition, prime number is a number which cannot be divided by any number except 1 and itself. Now, for 2 to be a prime number, we have to prove that in this ring, 2 cannot be divided by any other number except 1 and 2. Is that true? It is not true. Two is square root 2 times square root of 2. Both, that is, it's the same number square, and square root 2 is an element or is a number in this ring. Okay, so 2 is not a prime in this ring. Root 2 is prime. Okay, that's a good point. Is root 2 a prime? Suppose root 2 can be written as a plus b root 2 times c plus d root 2. That's a general form of two numbers. And in order to show that root number is prime or not, we have to just write it in this fashion and see if we can find values of a, b, c, d, satisfying. This implies that root 2 is ac plus 2bd plus ad plus bc times square root 2. This implies that ac plus 2bd is 0 and ad plus bc is 1. Okay, just multiplying out the right hand side and then equating. This is an integer, this is also an integer times root 2. So if this is equal to root 2, then the integral part must be 0 and this multiplier of root 2 must be 1. Okay? So what do we get out of this? This tells us that d is equal to minus ac by 2b, and here we get minus a square c by 2b plus bc is 1, and this gives us b square or 2b square minus a square times c is 2b. And a, b and c, all three of them are integers. So firstly, right hand side is an even number. So left hand side must also be an even number, which means a square c is because 2b square c is an even number, so a square c is an even number, which means either a or c is an even number. Okay. So now we have to do some bit of slightly messy argument. If a is an even number, then a square is a multiple of 4. Correct? And that would, okay, that's not a problem.
Let's just solution. We'll take b and c equal to 1 and a and b equal to 0.
B and c equal to?
B and c both equal to 1.
Yes.
And a and b both equal to 0.
And a and d to be 0. That will just give us that factorization. You are saying A and D are 0, B and C are 1, so that is square root 2 times 1. That's the solution. Sure, that is the solution. That's good to know. Is that the only solution? That's the question. And what I'm claiming, and I'll leave that to you to work out, is that the only solution in integers is that A is 0 as D and B equals C equals 1, or the other way, or A equals 1 equals D, B C as 0. And this will show that square root 2 is indeed a prime number. So prime numbers do exist, but they look different because 2 is no longer a prime. Similarly, 3 is not a prime because 3 I can write as square root 2 plus 1 times square root of 2 minus 1. 4 is certainly not a prime. It's 2 times 2, so not a prime. How about 5? Huh? Seems a prime? Seems a prime, yes. But this is getting to be painful in the sense that we have to, every element wise, if we have to go and see and verify if it is a prime or not, is going to be very difficult to really understand the structure of this. Can we come up with a more general result saying that this is the list of all primes? So that's one question. I don't expect an answer from you immediately, but fortunately it is possible to list down the list of all primes in this. And the way, again, if we have to do it listing first for z bracket square root 2, then for z bracket square root 3, then for z bracket square root of 5, again that will be a painful process. Ideally, for any z bracket square root of n, we would like to have a list of primes. And that is indeed possible. We can list down or come up with an expression for all the primes in such rings. That would resolve at least one question. But the other question still remains unsolved, which is, so suppose we have the list of all primes. Is fundamental theorem of arithmetic true? That is, every number can be uniquely written as a product of prime numbers. The answer is not necessarily. For example, let's consider z, and let me pick it up correctly now. Square root of minus 5. In this, one can show that 2 and 3 are prime. Z square root of minus 5 makes sense. It is same as z bracket square root of 5i. Okay, so it's a subset of complex numbers. In this ring, 2 and 3 happen to be prime numbers. Okay, and the proof is again of the same kind. You just express it in terms of a general product and see that the solutions are only trivial ones. But now I can write 6 as 2 into 3. So 6 is the product of 2 primes, 2 and 3. I can also write 6 as 1 plus square root of minus 5 times 1 minus square root of minus 5. So there is a problem. Even the look, maybe these are not prime numbers. One could say 1 plus square root of minus 5. Maybe it is not prime. If it is not prime, it will factor further into prime numbers. And this will also factor further into prime numbers. Eventually, all those, it will have at least 2 factors of primes. This will also have at least 2 factors of prime. So there will all be at least 4 prime factors. Whereas in here, there are only 2 prime factors. So there is no way these 2 factorizations are the same. They are equal, but they are not the same. So fundamental theorem of arithmetic breaks down here. And then suddenly there is a problem, because then it's not clear what exactly is the structure here. We have prime numbers here, but we can write each number as in multiple ways as products of primes. And that creates a problem. Okay, so these are the questions that immediately arise. So these are not, very strange rings. These are simply slight generalizations of the ring of integers. You put in one additional number, irrational number, in the ring of integers, that gives you another ring, which is a slightly bigger set of numbers. And there itself, the structure that existed in integers no longer exists. And there is this major problem that arises because that structure doesn't exist anymore. Studying rings of this kind becomes a challenge, because we cannot have that. See, having a unique prime factorization is a very nice property. Any number you can then write in terms of prime numbers and study those prime numbers, prime factorizations separately. But here, if there are multiple prime factorizations, then the one prime factorization may give you one thing and another prime factorization may give you another thing. And so it's not clear what should one do. So these are the challenges that almost immediately came about when we studied the ring of integers. And there is a very nice history, which I have run out of time, so I'll tell you about it next time, about the exactly why and how these rings of integers, these additional higher rings of integers, were discovered. And initially, actually, it was believed, without thinking much about it, implicitly, that fundamental theorem of arithmetic will hold everywhere. But that led to some very certain consequences which people believed to be true. And then at some point it was discovered that fundamental theorem of arithmetic actually breaks down. And if it breaks down, then all the earlier consequences were false. Okay? So that will form the beginning of the next lecture.